Good day, dear students. You are all welcome to Thermodynamics class. In today's lecture, we are going to be looking at the first law and its applications, as you can see what I have written on the board. So far, so good. In our previous lecture, we have discussed property, heat, work, and energy. But we have not related these forms of heat, energy, and work. We have not related it together. In today's class, we are going to be relating these two terms, heat and work. And the first law of thermodynamics helps in relating these two terms that I've just mentioned. A typical example of you, whenever you are carrying out work, you have to dispense a form of what? Heat. Then also when you are doing it, you have to do what? You carry out work. An example is when you rub your hands together, you are carrying out work, and the end result is heat coming out of it. The first law of thermodynamics states that whenever a system undergoes a cyclic change, however complex the system is, the algebraic sum of the heat transfer is the same thing as the algebraic sum of the work transfer. The mathematical expression of what I have just said is this. The algebraic sum of heat transfer is equivalent to the algebraic sum of the work transfer, which is also the same thing as summation of Q equals to summation of W. Now let's take an example to analyze the first law of thermodynamics, a closed system. As we all know that a system is a region in which thermodynamic analysis is being carried out. Let's consider it for four processes. We have Q1, W1, Q2, W2, Q3, W3, Q4, and W4 respectively. Going back to the first law that is expressed mathematically in this form, how do we get the summation of Q in this closed system that we are analyzing? Going back, as we have learned so far about the sign convention of both heat and work, whenever heat is done from the surroundings to the system, is taken as positive, and whenever heat is done from the system to the surrounding, is taken as negative. Also, when work is done from the surrounding to the system, is taken as negative, and when work is done from the system to the surrounding, is taken as positive. Now let's go back to the first law that is expressed mathematically. We want to look at the summation of all the heat transfer and the work transfer in this system. Now, Q is entering, Q1 is entering, W1 is entering, this one is taken as positive, this one is taken as negative, this is negative as it is being released from the system to the surrounding, this is taken as negative, this is taken as negative, this is taken as positive, and Q4 is taken as positive. Likewise, W4 is taken as positive. Then we go back to the summation. Summation of Q becomes Q1, which is positive, plus Q1, Q2, negative, Q3, negative, Q4, positive. Similarly, summation of W equals to W1 is taken as negative, W1, W2, negative, W3, positive, and W4, positive. When you equate these two together, you have it as the first law of thermodynamics that is applied to a closed system. Now, going back to the first law of thermodynamics, which is expressed mathematically, this expression can also become integral Q minus integral W equals to 0. What happened in this case? Why is it 0? Because there are no forms of what? Internal energy in the given system. As internal energy is taken as property, that is why the value tends to become 0. But in a situation where we are analyzing a closed system, also written in form of this, the cyclic integral, why the internal energy in this case becomes 0 is because of the cyclic integral of internal energy tends to 0. But in a situation whereby we are analyzing the heat transfer as well as the work transfer, which is the same thing as the internal energy, because we are looking at the cyclic integral, that is why the internal energy tends to 0 in this case. So the first law of thermodynamics can also be expressed as equation 2. This is equation 1. It can also be expressed in equation 2 the way we have presented it on the board, where Q is the change in heat, where W is the change in W, as well as the U is what? The change in internal energy of the system. Now the next thing that we are going to be looking at is enthalpy. Enthalpy, as we all know, is always designated or represented as capital H. It can also come in the specific form as a lower case of H. When it's coming in specific form, we have a lower case of H. And it is defined as the summation of internal energy and the flow energy. So this can be expressed as H equals to internal energy plus the flow energy, which is given as this. In the specific form, it can also be expressed as H equals to small u plus what? P small v. If the V in this case is the capital V, which is in terms of what? Meter cube. But the V in this case and the U in this case are represented as meter cube per kilogram, as well as kilojoule per kilogram at this level. Then for this, it is joule, and the volume for this is represented in meter cube. We want to look at another way by which we can also express the first law of thermodynamics, which is represented in equation 2 from the relationship of the enthalpy we have here. Going back to the closed system, where we have various forms of heat and work coming in and going out of the system, Q3, as heat is being supplied from the surrounding to the system, is taken as positive. So we go back to the equation and add a negative value. Now BV. When you differentiate this expression, you have the H equals to the U. This is a product rule, which is done in this manner: P dV plus V dV dP. Now for a constant pressure process, the P tends to 0. So we are left with the H equals to the U plus P dV. Now going back to the first law of thermodynamics in equation 2, let's name this as equation 3. Going back to equation 2, you can easily equate some of these terms. You will notice that the H is the same thing as the Q, which is in specific form. The U is the same thing as the U. Likewise, the W is the same thing as P dV. The next thing that we are going to do now is we want to try to get another form of relationship also from this expression, which will give us Cp, is also known as specific heat at a constant pressure. Then going back to the equation, H equals to U plus dV. Equation 3 can also be, you can also rewrite equation 3 in this manner. Follow the ideal gas equation, which states that PV equals to what? RC. So when you differentiate this, you have P dV equals to, since R is a constant, you don't need to differentiate it, it retains its value. So we have R dt, which means equation 3 is also written in this form. dH equals to du plus R dt. This is what will now take us to two key terms, which is known as specific heat at a constant pressure and specific heat at a constant volume. Specific heat at a constant volume is defined as the rate of change of enthalpy with temperature difference. So it is expressed mathematically as du equals to du over dt equals to Cv. The Cv here is called specific heat at a constant volume. So when you make du the subject of the formula, du equals to Cv dt, just keep this as equation 4. Then go back to the other specific heats. Don't forget, I said specific heats are of two different forms. C is divided into Cp and Cv. So we have done Cv. The next thing is to now define what Cp is, which is also known as specific heat at a constant pressure. And it is defined as the rate of change of enthalpy with the temperature difference. Cp in the mathematical form becomes dH over what? dt. Making dH the subject of the formula, dH equals to Cp dt. Name this as equation 5. Then go back to this equation and substitute equation 4 and 5. So we have dH is defined as what? Cp dt equals to du is now taking another form, which is Cv dt plus R dt. There is something that is common to both left side and right side of the equation and the right side of the equation, which is what? dt. So dt can be eliminated out. So the final form of this equation becomes Cv plus R. And R is defined as Cp minus Cv. Here, R is called the gas constant. And its SI unit is Joule per kilogram Kelvin. From this expression, equation 6, we can also play with some terms if we want to represent equation 6 only in terms of R and Cp. How do we go about this? We are going to look at another term, which is also known as specific heat ratio. The specific heat ratio is defined as the rate of change of specific heat at a constant pressure and specific heat at a constant volume. This is expressed mathematically as specific heat ratio is defined as the rate of change of specific heat at a constant pressure to specific heat at a constant volume. How do we express this? Specific heat ratio is defined mathematically as gamma equals to Cp divided by what? Cv. And this equation is known as equation 7. So now we are going to substitute equation 7. Since we want to make equation 7, we want to get another form of equation from equation 6. You know we have defined specific heat ratio to be equation 7. We want to express equation 6 in terms of only specific heat at a constant pressure and R. So going back to equation 6, which is given as R equals to Cp minus Cv. Here you are going to make Cp the subject of the formula. Cp becomes gamma Cv. So substitute this expression. You can name it equation 7a. Substitute equation 7a into equation 6. So we have R equals to gamma Cv minus Cv. Therefore, CV is common. We have R equals to CV into bracket gamma minus 1. So CV becomes R divided by gamma minus 1. Similarly, we can also express equation 6 in terms of CP. We make CV the subject of the formula since we want CP and R to come out. So going back, R equals to CP minus CV. Go back to equation 7. Make CV the subject of the formula. CV becomes CP divided by gamma. So substitute this in this. We have R equals to CP minus CP divided by gamma. The next thing we are going to do is to find LCM. So R equals to gamma CP minus CP divided by gamma. Take it to the other side. You have gamma R equals to CP is common into bracket gamma minus 1. So divide through by gamma. The equation becomes CP equals to gamma R divided by gamma minus 1. This is another form of expression which you can also derive from the difference between the two specific heats. Now let's solve a simple problem that is related to the first law of thermodynamics in terms of the cyclic integral Q equals to the summation of what? W, or cyclic integral W. Now we can pen down this question. A piston and cylinder machine contains a fluid system which passes through a complete cycle of 4 processes. During the cycle, the sum of all heat transfer is minus 220 kilojoule. Full stop. The system completes 120 cycles per minute. Determine the following table showing the method for each item and compute the net rate of work output. Now the table is illustrated on the board as process 1 Q. Change in internal energy U in kilojoule per minute. As the question is displayed on the screen, we are going to solve the problem now. Now, having gone through the 7 steps, which I told you in my previous video, that is the best way of solving problems involving STEM. So the first thing we are going to do is to list out the data in the question. Given, we were given the total heat in the system, which is given as minus 220. The total heat, QT, which is, or you can also write it as summation of Q, minus 220 kilojoule. Then the number of cycles in which the system performs is 120 cycles per minute. 120 cycles per minute. So what we are asked to determine, the further parameters are as shown on the screen. We are asked to determine, find all the missing values in the table. That is what we are asked to determine. Then the next step is to bring down some basic assumptions, which is the third step. Assumptions. The first assumption is the piston is the only work mode in the system. And the second assumption is friction between the piston and the cylinder wall is considerable. Those are the two key assumptions for this problem that we are solving. The next step is, what is the governing principle? The governing principle is, we have two assumptions which I have stated. The governing principle is the first law. The governing equation still goes back to the first law of thermodynamics, cyclic integral Q minus cyclic integral W equals to cyclic integral U, which is also represented as summation of Q minus summation of W equals to summation of U. Then the next thing is break out the schematic. Since it involves four processes, you can represent it on the PV diagram. Draw a system that involves four processes: 1, 2, 3. One, two, three, four. This is the schematic. And the next thing is to start analyzing the problem, which means we are about to start solving the problem following the governing equation. From process 1 to 2, we are given the heat, we are also given work. But the only missing term is the internal energy. Following the mathematical expression, making internal energy the subject of the formula from this, so we have change in U from process 1 to 2 equals to change in Q from process 1 to 2 minus change in W from 1 to 2. So going back to this, Q is what? 0. And W is given as what? 31220. So we have it as what? Minus 3120 kilojoule per minute. So we are done with process 1 to 2. The next one is to move to the second process, which is process 2 to 3. In process 2 to 3, we are also told to find the value of internal energy. So we can follow the same expression we have on the board. All we just need to do is just to change the processes. So the change in internal energy from process 2 to 3 becomes change in heat transfer from 2 to 3 minus change in W from 2 to process 3. So Q in this case is given as 22,500 minus the work done at that level, which is 0. So the final answer becomes 22,500 kilojoule per minute. The third process is process 3 to 4. What is missing in this case is the work done in the process. So we have Q and we have W. So what we are going to do in this case is to make W at this state the subject of the formula so that we can use it to determine its value. So going back to the governing equation, which is this, W from state 2 to state 3 to 4, change in W from state 3 to 4 equals to what? Change in Q from 3 to 4 minus change in U from 3 to 4. Now go back to the question as displayed on the screen. At this level, we have this to be minus 2,250 minus this particular value is taking negative, so it becomes positive. Minus minus become positive. So we have 38,800. By the time you punch your calculator, what is the new value that we are going to be having? $36,550. 36,550 kilojoule per minute. The next process is process 4 to 1. If you look at process 4 to 1, all the energy in interaction Q, W, and change in U, they were not given. So we need to determine that. Now for process 4 to 1, since the system completes 120 cycles per minute, what we are going to do is, if you notice that the units of Q, W, and U, they are in terms of kilojoule per minute. But the Q that was given in the question is in terms of what? Kilojoule per kilojoule. Then we are given cycle per minute. So what we are going to do in this case is to multiply kilojoule times cycle over what? Minutes. Then we have it as minus 220 multiplied by 120, which will now be what? What is the value? The value is minus 26,400. Minus 26,400. For process 4 to 1, for it, summation, go back to your first law of thermodynamics, we say the cyclic days, we are still going back to that. But let's look at the summation of all the heat transfer, which is given as this. Summation of Q. This value is for summation of Q. Summation of Q in this case equals to Q from process 1 to 2 plus 2 to 3 plus 3 to 4 plus 4 to 1. This is what we are asked to determine. Then the summation of Q has been gotten as what? Minus 26,000 minus 26,400, which is the same thing as for process 1 to 2. The value is what? 0 plus 2 to 3, 22,500. Then 3 to 4 is also given as minus plus minus 2,250 plus Q4 to 1. So when you punch your calculator, Q4 to 1 becomes what? What is the value? Minus 46,650 kilojoule per minute. The next thing we are going to look at is that of work done in kilojoule per minute. Before we go to work done, let's look at for internal energy. Since the cyclic integral of internal energy equals to 0, which means the summation of all the internal energy in the given system becomes 0. So we have U1 to 2 plus U2 to 3 plus U3 to 4 plus U4 to 1 equals to 0. So substitute all the values that you have gotten so far. U1 to 2 is what? The value is given as what? Minus 3120, 3120 plus U2 to 3 becomes 22,500. 3 to 4 minus 38,800. 800. Then plus U4 to 1. So So when you punch your calculator, what's the final answer? U4 to 1 becomes 19,420 kilojoules. Kilojoule per minute. So the final one is to determine the mathematical expression of the first law of thermodynamics. Summation of Q minus summation of W equals to summation of what? U. Or don't let us put it this way. Change in Q, change in W, change in U. So U, W at this level, take it to this side, equals to Q plus minus change in U. W from 4 to 1 becomes Q from 4 to 1 minus U from 4 to 1. This is the value of Q. Minus 4, 6, 650 minus the internal energy, which is what? 19,420. So when you add up these two values, what is the value? You are going to have what? Minus 66,070. 070. Is that all? You are going to add the units. Kilojoule per minute. Note, this is not what you are asked to determine. You are asked to determine the total work output in the system, which means the net work output summation, the net, equals to W1 to 2 plus W1 2 to 3 plus W3 to 4 plus W4 to 1. So you add up everything. 1 to 2 is given as what? 3120. W2 to 3 is given as what? 0. 3 to 4 is calculated to be what? What is the time? 3 to 4. What do we calculate the value to be? What? 36,550. And the last value is what? Minus 66,070. So when you do your calculation, minus 26,400. What is the unit? Kilojoule per minute. You can also take it to watts. Kilowatts, you can take it to kilowatts, yes or no? So what are you going to do in essence is divide it through by 60. So when you divide through by 60, what do you have? You can also be the same minus 440 kilowatts. So go back to the equation and insert all the values that you have calculated so far. So the value for this becomes what? 3,000 minus 3,120. What about this? 22,500. What about this? 36,550. It's 650. What about this? Minus 19,420. So we have come to the end of